Every time ask an AI to write a joke or like generate a picture of a cat riding a skateboard, you are actually physically boiling water.
You really are. It sounds crazy, but yeah.
Right. I mean, we always talk about the cloud like it's this magical, weightless software just floating in the sky somewhere.
Like it's completely intangible.
Exactly. But the reality is that the cloud is a deafeningly loud, fiercely hot, massive physical warehouse of steel and copper. And right now, that copper is literally melting under the pressure of our demands.
Yeah, the physical infrastructure of the internet is hitting a brutal thermodynamic wall right now.
Yeah.
We are just asking data centers to process and move so much information for AI that the traditional wires inside those buildings, I mean, they simply cannot handle the traffic without generating catastrophic amounts of heat.
Which is really the core mission of our deep dive today. So we're looking at a pretty fascinating stack of sources to figure out exactly how the tech industry is trying to escape this heat death.
It's a race, really.
It is. We have a product launch press release from the networking and laser technology firm Coherent. We also have a very revealing 2025 financial interim report from Sievers Semiconductors.
Oh, yeah, that one is super interesting.
It really is. And we're also pulling some deep in the weeds industry analysis from an issue of PIC magazine, PIC standing for a photonic integrated circuit.
Right.
So we are basically unpacking how microscopic beams of light are replacing copper wire, solving this massive energy crisis, and then eventually how they're bridging the gap to space satellites and autonomous cars.
Yeah, and to really understand the stakes here, I think we have to look at the sheer velocity of the problem.
Okay, lay it out for us.
So Yole Development, which was cited in that PIC magazine source you mentioned.
Yeah, the industry analysis.
Exactly. They project that the optical transceiver market is going to just blow past $24 billion by 2027.
Wow. 24 billion.
Yeah, and I mean, AI is the spark, obviously, but the fuel is everything else we do.
Like what specifically?
The Internet of Things. You know, our nonstop, ultra-high definition video streaming, global social networking. We are just demanding exponential growth from a physical infrastructure that is completely tapped out.
So think about it like pushing electricity through a standard copper wire.
Yeah.
You want to move basic email data, it's fine.
No problem.
But when you are trying to shove 800 gigabits or like 1.6 terabits of data per second, which are the speeds modern AI requires, it's like trying to force a thick, concrete-like milkshake through a tiny plastic coffee stirrer.
That is a brutally accurate analogy.
Thanks. I mean, the sheer physical resistance is enormous. Friction creates heat, and heat, as we know, destroys computer chips.
Right. So the industry is basically turning to lasers to bypass that friction entirely.
Lasers.
Yeah, shooting a beam of light down a fiber optic channel is like flashing a laser pointer down an empty, frictionless hallway.
So there's no resistance.
Exactly. The heat generation is practically zero. And Coherent is attacking this specific choke point with their new continuous wave distributed feedback indium phosphide lasers.
Okay, let's stop right there. Because continuous wave distributed feedback, indium phosphide lasers is just a wall of jargon.
Yeah, it's quite a mouthful.
I understand the laser part, obviously, but break down the rest of that for me.
Let's start with the material. Indium phosphide is a specific semiconductor compound.
Okay.
If you want a chip to do math or, route information, you generally build it out of silicon.
Right. Good old Silicon Valley.
Exactly. Silicon is cheap, and we have spent 50 years mastering how to use it. But silicon is fundamentally terrible at emitting light.
Just structurally.
Yeah, the physics of it.
Yeah.
Just doesn't emit light well at all. Indium phosphide, on the other hand, is a brilliant light source.
Oh, I see.
So you use indium phosphide to actually generate the laser,
Yeah.
and then you couple it to the silicon chips that do the work of routing the data.
Got it. Okay, but the press release also makes this massive point about these lasers operating in the O-band, specifically the 1310 nanometer region.
Yeah.
Why does the specific flavor or, wavelength of the light matter? I mean, if a laser is just a laser, why the 1310 nanometer exact spec?
It basically comes down to a physical phenomenon called chromatic dispersion.
Wait, chromatic dispersion, you mean like the cover of that Pink Floyd album where the glass prism splits the white light into a rainbow?
Yes, that is actually the perfect mental image.
Okay, but how does a Pink Floyd album cover mess up a server rack?
Well, think about how data is sent. When you pulse a laser to send a signal, say a pulse of light to represent a digital line, that pulse isn't a single mathematically perfect frequency.
It's not.
No, it actually contains a tiny range of wavelengths. And as that pulse travels through a medium, different wavelengths travel at slightly different speeds.
Ah, so they separate.
Right. If the pulse travels far enough, it spreads out, just like the rainbow exiting that prism.
Okay, I follow.
And if your one spreads out too much, it physically bleeds into the zero right next to it.
And then your data just becomes garbage.
Exactly. The signal is ruined.
So at 1310 nanometers, the light doesn't spread out.
Right. At 1310 nanometers, light travels through silicon photonics with virtually zero chromatic dispersion.
Oh, wow.
The pulses stay incredibly tight and crisp no matter how fast you fire them. And that is totally non-negotiable when you are building these massive 800G and 1.6T transceivers.
Okay, the physics totally makes sense now, but Coherent is really selling this on efficiency, right?
Oh, absolutely.
They claim their proprietary low-series resistance design gets 15% greater power efficiency compared to, like, whatever the industry standard is today.
Yes, 15%.
Let me play devil's advocate for a second.
Go for it.
15% better power efficiency sounds like a really nice bullet point for a marketing brochure. But is that really going to stop the AI data centers from melting down? I mean, it doesn't exactly sound like a silver bullet.
Well, you have to shift your perspective. In consumer electronics, yeah, 15% is incremental.
Right. My phone lasts an extra hour.
Exactly. Your laptop battery lasts an extra 45 minutes. But in a hyperscale data center, we're talking about a building the size of a shopping mall that draws as much municipal power as a medium-sized city.
That's a lot of power.
It's immense. At that scale, 15% is a seismic shift. We are literally talking about preventing the construction of entire new power plants.
Oh, okay, when you put it like that.
Right. But honestly, the 15% efficiency on the laser's primary power draw is actually the least interesting part of Coherent's announcement.
Wait, really? What's the real breakthrough then?
The real breakthrough is the secondary power savings, the cooling.
Which brings us back to boiling water. The air conditioning bills for these buildings must just be astronomical.
They are, but Coherent engineered this specific 70 milliwatt chip to operate completely uncooled.
Uncool.
Yes, up to a junction temperature of 85 degrees Celsius.
85 degrees Celsius is like almost the boiling point of water. You're saying they just leave this chip roasting inside the server rack without a fan or a heat sink?
Exactly. They allow it to run blisteringly hot, which means the data center operators can actually turn down those massive industrial air conditioning systems.
Wow.
The secondary power savings from not running the AC as hard are colossal.
So how did they do it? How does it survive that heat?
Well, Coherent's achieved this ruggedness by going into the active quantum well region, which is the microscopic heart of the laser where the light is actually generated, and fundamentally changing the chemical recipe.
Changing the recipe how?
They entirely eliminated aluminum.
Hold on, isn't aluminum the exact metal we put in laptops and engines specifically to dissipate heat?
Usually, yes.
So why is removing it the secret to surviving 85 degrees?
It's counterintuitive, right? Aluminum is great for structural heat sinks, but at the microscopic chemical level, deep inside a laser diode, it is actually a major liability.
Really?
Because under extreme optical power density and high heat, aluminum has this nasty tendency to oxidize. It reacts with trace amounts of oxygen and degrades over time.
Oh, I see.
Yeah, so an aluminum-based laser running at 85 degrees will literally burn itself out.
So by pulling the aluminum out of the active region, they fixed it.
Exactly. Coherent created a laser that actually thrives in the oven-like environment of an AI server farm.
And Coherent is obviously not alone in this race. I mean, the financial report we have from Sivers Semiconductors shows they are deploying a very similar strategy.
Yes, very similar.
They are sampling their own continuous wave distributed feedback lasers, specifically for the AI data center, quote-unquote, scale out.
And scale out is the absolute key phrase there.
What does that mean in this context?
We aren't just hooking up one computer to the internet anymore. Scale out refers to the optical interconnect layer that physically links tens of thousands of individual AI servers together.
So they act as one.
Yes, so they behave as a single unified supercomputer.
Well, Sivers explicitly notes in their report that they are anticipating a major supply crunch in the next 2 to 3 years.
Yes, they are.
And they expect their production to be fully online by 2027 to meet it. But if we have these magical aluminum-free lasers that solve the heat crisis right now, why aren't they in every server rack today?
Because building a flawless microscopic laser in a pristine research lab is relatively straightforward.
Okay.
Mass-producing tens of millions of them, cheap enough to deploy globally, That is a manufacturing nightmare.
Which takes us right into the bottleneck of how you actually build the physical internet.
Exactly.
Because Coherent is trying to solve this with brute force, it looks like. Their press release outlines this massive expansion to a 6-inch indium phosphide fab in Sherman, Texas, coming online in 2026.
Yeah, that's huge.
And this is designed to increase their production capacity by a factor of 5.
Yeah, moving to a 6-inch wafer is a massive deal in semiconductor economics.
Because it's bigger.
Right. You're baking these chips on circular wafers. If you increase the diameter of the circle, the total surface area grows exponentially.
You get more chips per batch.
Vastly more usable lasers per batch, which drives the cost per unit way down. But as PC Magazine details, printing the laser on the wafer only solves half the problem.
Because assembly is where the real bleeding happens.
Yes, assembly is the killer.
PIC Magazine throws out this wild statistic. They say 70% of a photonic device's total cost is tied up purely in assembly.
It's staggering, but think about what assembly actually means here.
Okay.
You have an optical chip emitting light, you have an electronic processor, and a literal glass fiber optic cable.
And you have to put them together.
You have to physically connect them. And the beam of light is a fraction of the width of a human hair. Historically, this required something called active alignment.
Active alignment, meaning like a human is sitting there with tweezers.
Not quite tweezers, usually a highly specialized robotic arm equipped with a microscope.
Still sounds slow.
It's incredibly slow. The robot powers the laser on, measures the light output, and micrometer by micrometer, physically nudges the glass cable until the light perfectly enters the pipe.
Oh my God.
And once the signal peaks, it glues it in place. It is painstakingly slow, highly prone to error, and catastrophically expensive.
That makes POET Technologies' solution sound like pure science fiction then.
It really is a game changer.
Because PIC Magazine highlights a POET optical interposer that uses a CMOS-based design for wafer-scale passive assembly.
Right.
They claim this drops that 70% assembly cost down to just 20%. I need you to translate wafer-scale passive assembly for me. How do you connect microscopic light pipes without nudging them into place like you just described?
By building the alignment into the floor plan before you even drop the laser in.
What do you mean?
Okay, so CMOS stands for Complementary Metal Oxide Semiconductor. It's the standard, deeply mature manufacturing process we already use to print everyday computer chips.
Okay, the standard way.
Right. POS uses this standard process to etch microscopic, highly precise canyons and waveguides directly into an interposer layer, which is basically a foundational base plate.
So instead of a robot trying to balance a cable in front of a laser, the base plate already has the exact grooves carved out.
Yes, you just place the laser into the microscopic trench. The physical geometry of the trench actually forces the laser into perfect optical alignment with the waveguide.
So no powering up?
No powering up, no nudging, no measuring. It passively snaps into place.
That is wild.
And because it's done at the wafer scale, you can assemble thousands of these connections simultaneously in a single manufacturing step, rather than doing it one by one.
Wow, we are essentially 3D printing the connections.
Basically, yes.
And Sivers Semiconductors is already leaning into this. Their report notes they actually sampled POET with their lasers, specifically for POET's optical engine.
Exactly. Sivers provides the horsepower, POET provides the packaging.
It's a tag team. And PIC Magazine highlights another tag team tackling the hardware bloat, Max Linear and Dust Photonics.
Yes, another great example. They combined forces to integrate Dust Photonics' low-loss laser coupling technology, or L3C.
What does that do?
It is a wildly efficient way to couple the light into the photonic integrated circuit without losing signal strength.
And because it's so efficient, they actually figured out how to use just one laser to drive 4 separate data channels in their 400G and 800G modules.
Which is huge.
I mean, they cut the actual number of lasers required by 75%. That is just a brutal, direct way to slash the bill of materials.
Well, less hardware means less power draw and fewer points of failure.
Makes sense.
And the global realization of how critical this is has actually triggered massive state-level intervention.
I mean, governments are getting involved?
Big time. Europe is absolutely terrified of being left behind in this manufacturing race. Photon Delta just secured 1.1 billion euros in public and private funding to build a pan-European integrated photonics supply chain.
1.1 billion euros.
Yeah, their stated goal is an infrastructure capable of churning out 100,000 wafers a year by 2030.
The scale of the money is staggering, but I want to look critically at the finances of the companies actually doing the building here.
Fair enough.
Let's dig into Sivers Semiconductors' 2025 financial report. Because they boast about record Q4 revenues of 80.7 million Swedish krona and full-year revenues of 304.1 million SEK, which is up 25% year over year.
Sounds pretty good so far.
Right, and they highlight a total opportunity pipeline that surged 64% to $453 million. Sounds fantastic on page 1.
Well, page 2 is usually where the reality of deep tech sets in.
Yeah, because page 2 shows their operating profit, their EBIT, was a loss of 141.3 million SEK.
It's a big number.
That is a massive hole. Are these photonics companies actually viable businesses, or are we just looking at highly expensive science experiments that are burning through investor cash?
I get why you'd ask that, but it's the classic valley of death in deep tech scale-ups.
The valley of death.
Yeah, what you are seeing is not a failing business. It's the financial anatomy of a company transitioning from a research and development lab into a heavy industrial manufacturer.
Oh, because scaling is expensive.
Insanely expensive. Capturing a slice of that future $24 billion market requires massive, agonizing upfront capital expenditures today.
You have to build the factory before you can sell the widget.
Exactly.
And Sievers defends the negative EBIT by pointing to strategic investments in R&D and aggressive sales expansion. Like, they specifically call out hiring Raymond Bayagan as their new chief revenue officer to aggressively target the U.S. and China.
Which is smart, because you can't land a massive hyperscaler contract without a global support infrastructure already in place to service it.
Right.
But the report also highlights a non-cash foreign exchange loss of 31 million SEK. That part is critical to understand.
Wait, a non-cash loss, meaning they didn't actually spend that money.
Correct. It is purely accounting math on a balance sheet.
How does that work?
When a Swedish company operates globally, they hold internal funding in US dollars and British pounds. When the exchange rates fluctuate, the paper value of those holdings changes when converted back to Swedish krona.
So it looks bad on paper.
It impacts the official profit margin? Yeah. But it doesn't mean a single actual dollar bled out of the business operations.
Got it. And really, the ultimate proof that this isn't just a science experiment is tucked away in their defense contracts.
Oh, absolutely.
Sievers received TRL-6 approval from the U.S. Army for their user terminal solution. And TRL stands for Technology Readiness Level.
And let me tell you, the U.S. military does not hand out TRL-6 to theoretical concepts.
No.
No. Level 6 means the technology has been ripped out of the lab, built into a prototype, and successfully validated in a relevant end-to-end physical environment.
So it's real.
It means the technology is rugged, it works, and it is ready to transition into full production.
Which perfectly bridges us to the final act of this deep dive. Because these lasers are now so incredibly rugged, heat-resistant, and cheap to package, they are basically escaping the data center entirely.
They're going everywhere.
Sievers announced a $6.6 million U.S. CHIPS Act contract for electronic warfare.
Huge.
Right. And multiple European SATCOM vendors are moving to the request for proposal stage for the IRIS-2 satellite program using Sievers hardware.
Yep.
Plus, they're projecting a massive automotive LiDAR deal worth $28 to $53 million between 2026 and 2030.
I mean, just think about the environmental demands of a fighter jet, a low Earth orbit satellite, and an autonomous car driving through a blizzard.
They're all terrible environments for electronics.
Exactly. They all require hardware that is incredibly lightweight, sips power, and can withstand violent physical shock and extreme temperature swings.
Which brings us to the exact crossover we see in the 28 million euro QIRO project in Germany, which was featured in that PIC magazine piece.
Right, the QIRO project.
Trump, Bosch, and the German Aerospace Center are teaming up to use quantum technology-based sensors for miniaturized satellites. They are essentially taking the exact same photonics concepts that are keeping ChatGPT servers from melting down and using them to align mini satellites in space.
And the demands of space are brutal.
Oh, I'm sure.
A satellite experiences blistering, oven-like heat when it's in direct sunlight, and then it plunges to near absolute zero the moment it passes into the Earth's shadow.
Talk about thermal shock.
Right. Traditional electronics warp. They degrade, and they drift under those extreme thermal changes. So Trump brought a specific component to solve this, a 795 nanometer single-mode VCSEL.
Okay, VCSEL stands for Vertical Cavity Surface Emitting Laser.
Yes.
And from what I understand, instead of shooting light out the side of the chip, it shoots it straight up from the surface.
Right, vertically.
But Trump is bragging that their new VCSEL hits 10 milliwatts of power, which is 10 times higher than previous iterations. Why does a satellite need a tiny laser to be 10 times louder?
Because they're using these lasers to drive quantum sensors for attitude control.
Attitude control, meaning direction.
Essentially, microscopic gyroscopes that tell the satellite exactly how it is oriented in the vacuum of space.
Okay.
To calculate attitude using quantum mechanics, you need a beam of light that maintains absolute spectral purity and stability. Any thermal wobble ruins the math completely.
Ah, so a stronger beam helps.
A 10 milliwatt VCSEL provides a beam that is powerful and stable enough to survive the thermal shock of space, allowing these mini satellites to securely lock onto each other and form high-speed data meshes in orbit.
Wow. And as the PIC article points out, that exact same immunity to temperature swings and physical vibration is exactly what Bosch needs to build highly precise gyroscopes for autonomously driving cars here on Earth.
Yes, the physical infrastructure of our world, from the server rack to the highway to low Earth orbit, is just quietly transitioning from moving electrons through copper to moving photons through silicon.
It is a massive structural pivot, and it's happening entirely behind the scenes.
Entirely invisible to most people.
And we've covered the full spectrum of that transition today. We started deep inside the suffocating heat of the AI data center, looking at how Coherent's aluminum-free indium phosphide lasers are saving massive amounts of power by just running hot.
At 85 degrees.
Right. And then we broke down the manufacturing bottleneck, seeing how POET Technologies' interposer uses CMOS techniques to basically 3D print optical connections, dropping assembly costs from 70% down to 20%.
And we tracked how that scale-up phase, despite creating short-term accounting losses for companies like Sievers, is really cementing the foundation for a defense and aerospace revolution.
Right.
Integrated photonics are finally rugged enough to guide missiles, align satellites, and steer our cars.
So the next time you stream a 4K video to your phone or marvel at how fast a massive language model returns an answer, just remember the invisible microscopic laser grids making it all happen. They are the silent, friction-free bullet trains replacing the melting highways of the old internet.
Beautifully put.
Thank you. But there is one final provocative question I want you, the listener, to walk away with today.
We focused entirely on the macro scale today, right? Hyperscale data centers, military satellites, global telecommunications networks.
Exactly. But if integrated photonics are entirely replacing traditional electronics in the world's most demanding environments, how long until this tech shrinks down to the microscale?
That's an interesting thought.
Could we see a future where the everyday consumer devices we rely on, the smartphone in your pocket, the smartwatch on your wrist, the laptop on your desk, just abandon electricity and run entirely on light?
No more batteries overheating.
Imagine a computer processor that literally cannot overheat and a battery that doesn't degrade because there is no electrical friction slowly destroying the components.
It sounds like sci-fi,
But the tech to do it is already orbiting above our heads. It might just be a matter of time before it ends up in your pocket.